Hi there. Welcome to Lecture 8 of Machine Learning from Data. We're going to be talking about linear models, specifically linear classification and linear regression. Okay, now, we've spent a lot of time and energy, on some theory, and large amount of that theory was to establish the first step in machine learning, which is that E in can be made close to E out. Okay, and we studied this approximation versus generalization trade-off. Okay, and that's absolutely fundamental. It's always there, and you have to ensure the first step of learning. And today, we'll spend a little bit of time sort of addressing the E in close to zero issue, because if you spend all this time and theoretical energy establishing E in is close to E out, but you don't manage to get E in close to zero, then it's all for naught. Okay, so we need both. Okay? And today we'll spend a little bit of time discussing the E in issue, E in close to zero issue, specifically in the context of linear models. It's a very powerful model. Okay, so let's just recap. Okay, so where we were up until the last lecture. So we've sort of finished this theoretical tour de force where we developed this VC theory that applies to infinite hypothesis sets and establishes the link from E in to E out. So E out is at most E in plus a complexity error bar omega of dVc. So there's this VC dimension that summarizes, that captures the complexity of a hypothesis set with respect to its ability to fit data. Okay, basically, and in this formula is embedded the sort of approximation generalization trade-off, which is, E in is how well did you fit your data, and you'd like a large hypothesis set, a large VC dimension in order to ensure fitting the data well. But then how confident are you that E in will generalize to E out? You'd like a small hypothesis set, a small VC dimension. And that's summarized in this curve here, where if we plot on the x-axis the VC dimension, the in-sample error will gradually be dropping as you increase the complexity of a hypothesis set, as you increase its VC dimension, and that's because I get to pick the hypothesis G from my hypothesis set. So if you give me more options, I'll be able to fit the data more easily and get a lower in-sample error. Okay, but as you increase the VC dimension, this omega of the dVc is increasing, and so the bound on E out will typically have this U-shaped behavior, and that sort of implies that there's this optimal VC dimension, dVc star, and that sort of sets a fence around what you can do in order to establish that E in is close to E out. So you want to use a hypothesis set of this VC dimension, this complexity. And then the question becomes, well, how to choose? There may be many hypotheses sets with that complexity, so how to choose one? And that's a lot of the effort that machine learning expert has to bring to the table, which is to understand that you can't just use as big a hypothesis set as you want. The size of this hypothesis set dVc star will depend on the number of data points that you have available, and based on that number of data points, we have a complexity. Now there are many choices with that complexity. Which one should I choose? Okay, and we'll just discuss a little bit of that today. Okay. Now, on the other side, we discussed another view of this trade-off, okay, which is the bias variance analysis, which is also a breakdown of the out-of-sample error into two terms, the bias and the variance, and therein lies this approximation generalization trade-off. Okay. And the bias variance analysis is able to take into account the algorithm that picks the final hypothesis, but it only applies to the squared error. And it breaks down the out-of-sample error into two terms, just like the VC analysis. It says that your out-of-sample error is, the sum of two terms, the bias, which roughly speaking corresponds to how well can you fit the data, as opposed to the VC E in, which is how well did you fit the data. Okay, so the bias is how well can you fit the data, and as you have a larger and larger hypothesis set, as we have a larger and larger VC dimension, your capability for fitting the data, i.e. your ability to approximate the target function, increases. So it's similar to how the in-sample error behaves when you increase your hypothesis set complexity. Okay, so we would like a large hypothesis set if we want to get the bias small, but unfortunately, as you do that, as you use a larger and larger hypothesis set, there's this best hypothesis in there, but when you generate a finite data set, you can't find it. You'll output something around that, because with one data set, then with another you might output something else, and so on and so forth. So there's this variance around that best you can do that, comes from the randomness in the data set. And the larger the data set, the less that randomness. Okay, so this variance term also comes in. And now, the smaller the hypothesis set, the smaller the variance will be. And the out-of-sample error is the sum of these two, and there's the trade-off. you want to get both the bias and the variance small, which means you want to choose a large hypothesis set to get the bias small and a small hypothesis set to get the variance small, and there's the trade-off. Okay. And we saw that in an explicit concrete case of learning this blue target function with flat lines or lines with slope. Okay, the flat lines, slightly simpler hypothesis set, more constrained, less able to fit the target function, and so therefore the bias is large. Okay, but by virtue of that constraint, by virtue of being simple, the variance is small. There's not much variability in what's output, and when you look at the bias plus the variance, it's whatever it is, 0.75 in this case. Okay. The more complex hypothesis set with sloped lines, look at the wildness. This is coming because when you generate two data sets, a data set of 2 points, almost anything can happen, and you get sort of a wild-looking array of lines. Okay, but on average, you will get this red line, and on average, it fits better than the flat line. But the variance is huge, as indicated by this gray region. Okay, and so when you add up the bias and variance, because that's a theorem. The expected out-of-sample error is the bias plus the variance. When you add those two up, you find that the simpler hypothesis set wins by virtue of having much smaller variance, even though its bias is high. Now, if you increase the number of data points, okay, that tends to control the variance. Okay? And if you increase the number of data points, then the slightly more complex hypothesis set in this example wins. If you had 5 data points, the slightly more complex lines with slope wins by virtue of the fact that it maintains approximately the same bias, okay, but its variance shrinks a lot, and then the bias plus variance beats the bias plus variance for the flat lines. Okay. Now, I want to come back to the theory, before we move on. And let's revisit the VC theory, because I want to first tell you how general it was. I mean, that was just, any target function, any hypothesis set, any algorithm that picks a hypothesis from the hypothesis set as your final hypothesis G, and any input distribution P of X that's generating the data. Okay, so it's completely general. It applies to any machine learning problem. Okay, and you can, in principle, get this link from E in to E out for any machine learning problem. That's fantastic. But, so this is a warranty. This bound that links E into E out is a warranty, and this warranty has certain conditions for not being void. You will void this warranty if you violate those conditions. And what are those conditions? They're simple conditions, okay? But believe me, people always violate these conditions, even though they're simple conditions. Okay? So what's the first condition? Okay? You cannot look at your data before you choose your hypothesis set. Okay? It's a very simple condition. Okay? And it looks very constraining, but a long time ago we said it's without loss of generality. But it has to be fixed ahead of time. And then, now that we have this trade-off, we see, okay, that since you have to fix it ahead of time, that introduces the possibility of failure. Okay? It's possible that now you fixed it ahead of time, and you managed to get E in close to E out, but E in was large. You failed. Okay? So this notion that you have to fix the hypothesis set before you look at the data introduces the possibility of failure. That's fundamental. You can only learn if it's possible to fail. Okay? Now, that condition is violated all the time, and people are misapplying the VC analysis, thinking that, I only need to apply it when I use the big hypothesis set. But if you're going to, use the following kind of workflow, let me try a simple hypothesis set. Oh, it succeeded. Fantastic. I'm done. I can use the VC analysis, blah, blah, blah. Oh, but it failed. Now let me try the more complex hypothesis, and that succeeded. Oh, well, I know that I have to apply the big VC dimension. Okay, that's true. You have to apply the big VC dimension whenever you try a more complex hypothesis set, but you have to apply that big VC dimension also for the case where the simple hypothesis set succeeded. So it doesn't matter whether you search your ultimate huge hypothesis set sequentially or all at once. It's the same bound. Okay? The bound is sort of giving you a safety net. It's controlling the probability that you will be in trouble for the entire process that you are implementing, the entire process up to the stopping condition when you say fail. Okay. The data must be generated IID. Okay. Now, you need that in order to apply the Hufting bound that allows you to conclude that E out is close to E in. Okay. It's essentially something like a law of large numbers. Okay. That's usually not so hard to abide by. So your data is coming from some, data generating process, and each data point is coming to you IID. Usually not hard. What's hard is to ensure that the data and the test point that you're going to be tested on come from the same P of X, the same bin, essentially. So we sort of phrased this long time ago by saying that if you take a sample of marbles from a bin, look at the fraction of red in the sample, you can only say something about the fraction of red in that same bin. You don't poll in Australia and try to predict the election in the USA. Okay? And those are the same issues that are at stake here when you're looking at generating your test point. So it must be the case that your data is generated from the same distribution that your test point is coming from. And we may ask, what happens if these assumptions, these conditions are violated? Does it mean that, the VC analysis is approximately true if I approximately violate these conditions? Anything can happen. That's the Wild West now. Okay. There's no almost violating these conditions and an almost void VC warranty on E out. There's no such thing like that. If you violate the fact that the training data are not coming from your test distribution, we have no idea, what's going to happen to your E out. And it's just like saying, does polling in Australia give me some idea about what's going on in the election in the USA? Probably not. Okay, it's a totally different, can of people. Okay, so you cannot violate these assumptions. If you violate these assumptions, you will pay the price, and that price can be huge. And later on in this course, we will see examples of when these assumptions are violated, and we're done. Okay, so that's the theory of approximation and generalization. There are a number of conditions, best practices or essential practices for how you generate the data and how you sort of approach generating the final hypothesis. You must satisfy those. Now let's move on to the linear model. Let's talk a little bit about how we get E in small, in particular linear models.